Okay, so you have the Earth is a distance of 1.49 times 10 to the 11 meters from the Sun. Yeah, I changed it from kilometers to meters. And the time is 365.25 days. Use this to calculate the mass of the Sun. So if you go to your formula book,
there's no R of the small g.
wait, it's going to be, whoa, slow on. It's going to be one of Kepler's formulas, which is, let me get it here, dude,
Alex.
Chris, Boris. Please, I'm looking here. There it is. Is it? No, sorry. No, it's not here. It was in the other formula book, I think. Anyways, we'll have to work it out bit by bit, so. Okay. Oh no, I have the formula here, but it's not in the formula book. But if you check the 2013 exam, please make sure it's in the new formula book so you don't have to remember it. But I'll write it down here anyways. The formula is, and this is Kepler's third law, T squared equals 4 pi squared over gm times r cubed. Yeah.
Is it recording?
Yes. It's recording. I know there's usually a red box around the edge, but it doesn't seem to be there today. Actually, I can make sure the other ones worked. This is weird because it'll be a recording of the recording. Yep. Then in the next video, if I open up the last video, there'll be a recording of a recording of a recording. Inception style. Right. Now, in this, what do we know? Well, we know the t, but we have to be careful. We should change the t into seconds. Do we know the r? Yes. Do we know 4 pi?
How do we know they are?
That's this here.
Oh.
They're looking for the n here. So look, I won't bother doing this because it's straightforward. After a little bit of algebra, the n comes out as 1.97 times 10 to the 30. Okay. I would actually prefer if people were writing, because I feel like there's too much distraction when you're not writing. So I will continue when everybody has pen and paper out. I know I'm recording this, but you will remember it better if you write it down also. Pen and paper. If you don't have paper, I have some here you can use the back of. Okay? It's not a problem. I'm happy to accommodate, yes. Please hand this over to Bilal. Alex. You have paper? Anyone else need paper? Chris has paper.
I have a book.
Chris doesn't need paper, he has a photographic memory.
Yeah, right.
But I think the lens is broken. Right, that's part 1. Part 2 now is he wants the density, which is mass over volume, which is 1.97 over 10 to the 30, and then the volume is 4 over 3 pi r cubed, and he gives you the r in the question. Well, in fact, he gives you the diameter, but the r you just divide by 2 times 10 to the 9 squared, which works out as 1397 kilograms per meter cubed. Okay, give you a moment to write that down. I think that this has been the easiest exam so far, I think. That is the reason why I used that one as your end of semester 1 exam. Okay. Next one is calculate the gravitational field strength. Do you have a formula for that? It's gm over r squared. Well, we know the g, we know the m, and we know the r. I think a common mistake people maybe made here in the exam was use the wrong radius. I don't remember. Anyways, this comes out as 272 meters per second squared. So you can see if you are on the surface of the sun, you have a great deal more acceleration. Okay. Is that okay? Yeah. We'll go on to the next piece now. So next piece, the radiation from the sun is 1.37 kilowatts per meter squared at a distance equal to the Earth's radius. Show that the total amount of energy released from the sun is that. So what you have here is sun, and there's radiation coming off it, and then by the time it gets to Earth, the intensity is 1.37 kilowatts per meter squared. So in other words, for 1 meter squared, you get 1.37 kilowatts. So let's work out how much energy you get in total. So there's like a giant ball around the sun, and the energy would be the area of the ball multiplied by 1.37 multiplied 10 to the 3 because of the kilo. Now, who knows the formula for area of a sphere? I don't think it's... No, I don't think... Yeah, I just think it's 4 pi r squared. It's at the start of the formula book. No? No, that's the volume. Yeah, be quiet, Chris. Oh, actually, I have it here. What am I doing? 4 pi r squared. Yeah. Multiply that. Anyways, the radius you use here is the big one. The 1.49 times 10 to the 11. So when you put those numbers in, out comes 3.82 times 10 to the 26 joules. Cool, dudes? Yeah. Write that down, please. Got it? Yeah. Okay. Now, part C. You have this process inside the sun. What happens inside the sun is 4 hydrogen 1 atoms fuse together. Do you remember this word, fusion?
Yep.
And out comes a helium-4, plus some energy. Now, before this process takes place, the mass here is, you're told, is 4 times 1.0073 U, where U is roughly the mass of a proton or a neutron, it's atomic mass. Afterwards, you're left with the mass of helium, which is this. So you can see, in fact, if I multiply this by 4, it'll be a little bit bigger than this. I would like to know how much mass is lost. So, oops. So the lost mass would equal that minus that. Which turns out to be, when you substitute in what the U is, and when you do the subtraction, this works out as, I have it here, 3.98 times 10 to the minus, 4.42 times 10 to the minus 29.
Can we just express it in terms of U?
No, because in the next part you need to have it in kilograms for the next formula. So first you can express it in terms of U and then in kilograms. That's roughly the mass of an electron, isn't it? Isn't an electron? No, electron's minus 31. So what is it roughly the mass of? Anything that we know? It's smaller than a proton or a neutron, but it's bigger than an electron. So anyways, it's not that big. It's smaller than a proton, neutron, but bigger than an electron. So in between. Anyways, that's how much mass is lost, but we want to know how much energy is made. Where does this energy come from?
Fusion.
Yeah, which formula? It comes from the lost mass. So what's the formula? E equals mc squared, which equals, well, in this case, delta mc squared. 4.42 times 10 to the minus 29 times 3 times 10, 8. Thank you. Squared. 3.98 I have in the marking scheme here, but whatever. 3.98 times 10 to the minus 12 joules. Doesn't look big, but in fact, because it's only 4 protons turning into helium, you can see it's many, many times bigger than the units you use for the mass of what you're dealing with. So it's actually pretty big. The next question is, determine how many of these must take place per second. Well, we have from an earlier B question what the total energy is. Where is it? There it is. So just take this and divide it by this to get how many you have in total. So the number of these processes that take place is, where's it gone? 3.82 times 10 to the 26 divided by 3.98 times 10 to the minus 12. What's that, Brandon?
9.59.
In the marking scheme, I have roughly 9.6 times 10 to the 27.
How many decimal points do you? Or SF?
More is better, but like the marking scheme seems happy to go with 1 decimal place, but sometimes it goes with 2. So I'm not really too worried about it. If you're not sure, just go with 2. I'll be fine with that. Now, next one is interesting. How much mass is lost per second? Okay, so this is how many processes must happen per second. And this is how much mass is lost per second. So just multiply the two. So the lost mass equals the number of these processes multiply how much mass is lost in each process, which we have, what did we have earlier as? Come on, help me out here, you're writing this down. 4.42 times 10 to the minus 29. And then how many processes are happening per second, Brandon?
9.6 times 10 divided by 7.
So how much mass is being lost per second?
4.2 times 10 divided by 7.
You sure about that? This is what it's coming up in the marking scheme as. Can you double check that, please? Wait. 109? Hang on. Something went wrong here. I think this is a typo actually in the marking scheme, because they have determine the lost mass. It's 9.6 times 10 to the 37, and then you should multiply it by how much mass is lost per process. I think they put the wrong number in here. They said 109 kilograms per process, but instead, no, that's not right. Forget that. Sorry. So what did you get, Brandon?
The same one, but power of 9.
Power 9. Okay. Unless they used grams earlier. Sorry, let me check. No, that's joules. That's kilograms. Yeah. Don't know. Don't know. All right. Last part of this question. The sun can lose 4%. Oh, this is per second. The sun can lose 4% more of its mass before this process stops. How long until this happens? So 4% of the total mass, that equals 0.04. What's the total mass of the sun? We've got 1.97 times 10 to the 30. So that equals 4.24 times 10 to the 11 kilograms. So that's how much fuel it has left to burn. So the time would equal this divided by how much it burns per second, which is 4.24 times 10 to the 9. What's that? Is that right?
I think
Something went wrong here.
4% is wrong. 4.24 times 10 by 11.
Yeah, that's what I have here.
Is it right?
Is it? Sorry, you have the calculator there. Is that wrong?
Yeah.
Of course it's wrong. Sorry. What is it?
7.88.
I'm sorry. I misread the answer. What is it?
7.88.
No, I was worried because this seemed like a very small number. I'm like, oh man, we're screwed. The sun's going to burn out soon. What is it?
7.88.
7.88 times
10 by 28.
28. Oh, that's better. So here, 7.88 times 10 to the 28.
1.86.
Yep.
Times 10 by 19.
10 to the...
19.
That's better, isn't it? How many? Yeah, that's better. How many years is that? That's quite. Oh wait, now this is seconds. So give me the calculator and let me change this into years, okay? This is in seconds. Right, so if I divide this by 60, I now have minutes. If I divide it by 60 again, I now have hours. If I divide by 24, days. If I divide by 365.25, I have years.
5 points.
So this is 5.89 times 10 to the 11 years, which is the answer they have here. Which is, how many zeros? 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's just say that's about 6, roughly. So that's 600 billion. No, is that right? There's million. No, sorry. Here's million and here's billion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's actually. No, that's actually longer than I thought. It says here 6 times 10 to the 11. Is that 600 billion? Do I have too many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Here is 1,000 years, million years, billion years. 600 billion. Yeah, no, that's the answer they have here in the marking scheme, but I think that's way too big. 600 billion?
I think it was 10 billion.
Yeah, I always like 10 billion or something is what I was picturing. There must be something that happens that speeds up the process when it runs out of more fuel, or it's something drastic happens. Yes, actually, that's what's happening. This assumes that it just burns up the fuel continuously. Okay, it won't do this. In fact, what will happen is if the fuel burns up, gets a bit cooler, and then it expands. Okay, so in fact, I think yes, maybe the sun will continue to burn for 600 billion years, but I think for people on Earth, there's going to be a problem when it expands. And you know about this? You know what it's called when the sun expands, when it cools down? Yes, actually the name of the process of expanding. So you have your sun, and then it starts to burn up its fuel, and then it expands, and then continues to burn up its fuel. It's called a nova. Supernova is actually something different. I'll tell you the difference in case you didn't know. With a nova, the sun burns. Hey,
are you the teacher?
yeah. I'm talking here. All right. With a nova, the sun continues to burn, and then it cools down, and then expands. Okay. Or does it heat up? I want to get this the right way around. Yeah, that's what happens. It burns up the fuel, and then it expands. Okay? And the reason this happens is, look here, here's your sun. Look here, Bilal, here's the sun. There's two forces at play. What are the two forces? Gravity pulling it in, and
pulling it up.
And you saw what?
yes, no, I've been waiting for Irish students to tell them to go to Sylvia, but I'm guessing you're coming back. No.
Earth pulling
Sit
it
down.
up.
Wait,
What?
well, that actually is one of the forces, but it's not that big. Hey,
Not more.
no, that's an important force. Is the Earth pulling it out? It's small, but it's important. Right.
Still on the Earth.
Please, I'd like to continue. Now, as I was saying, here is our sun here. There are two forces. What's the force pulling it in? Gravity. But what happens when something gets hot? It expands. So it wants to expand because of the heat, and gravity wants to pull it in. If it's burning up its fuel and it loses mass, does the gravity get bigger or smaller? Smaller. So then, is this balanced? No. This one will be bigger than this. So because this will be bigger, it will then expand out. And then the Earth, I'm pretty sure when the sun goes nova, that's what this is called, the Earth will get sucked in.
The sun's
Yeah. Now, the question said there's 800 billion years of fuel left, but I think there'll be a problem before that, and the problem will be the sun will eat the Earth.
But there will be a problem then. By then human beings will have been extinct.
Or at least have relocated to another planet, yes.
Well, I think
Now, Bilal used the word supernova, which in fact is a little bit different to this. This is called a nova. In a supernova, it's the same thing, that it expands, but the difference is so much mass is lost and it's so hot, it expands so quickly that it keeps going. And it's like a shock wave that it just kicks the surface off and just expands out into space. So you'd have this sun here goes nova, and it's like if you picture it like this. This is the sun, and then when it expands, it's going so fast that gravity can't pull it back, and it just shoots out. You see a bright flash, and then what's left is this tiny, tiny little shell, much smaller and much colder. This here is called a red giant, I believe.
Yeah.
And does anyone know what this cold piece left behind is called? White dwarf. Very good. And last one, if it's really, really big, after supernova, there won't be a white dwarf left. And yes. And yes, you'd be pretty screwed if you were nearby. Right, that was number 3.
So